For the following the next 25 minutes or so, just briefly introduce the current and recent development of regional earthquake site response simulation and analysis in R2D, and specifically, we can start to put up together a workflow that can run through, as Professor Derna mentioned, from earthquake scenario pickup and then seismic analysis going into the rock level, and then soil response analysis, propagates those events to the surface, and then continue the building response and the damage loss assessments. And specifically looking into Alameda Island, which is in the Bay Area, to see if we could have a concrete example to show with you. And I will start with the, again, this figure just to displayed several times in in today's workshop. But for specifically, it's a modular feature that we can utilize here is that when we look into Alameda, for instance, the site response analysis, we put together a few of pieces of in the map and try to link the entire workflow. So today, I'm just going into each of these 4 steps to introduce some of the basic details about our modeling, current adaptations, and extensible places that we are also very welcome your contribution and thoughts, and tell us about how you feel about this workflow and what can be done in the future, and to really upgrade the entire capacity of this workflow, as well as its future impacts as well be covered in the end to propose a Alameda test bed. Here I'm just showing each individual step. Let's go into the first part is the building inventory. We call it BIM, Building Information Model. And this is in the Alameda testbed, as Stephen has showed in the previous talk, that we have a very detailed building inventory model thanks to our SimCenter researchers. And it's including across to 15,000 buildings and across different year builds and different construction types and the occupancy types. And let's get down to the ground to see what's the hazard that really dominated this Alameda site. So for this example, I will go to show you later in the presentation. We have to identify 177 sites on the island itself. And then we try to first get the surface ground motion, but there's 2 ways. So basically, the first one is really very empirical methods based on the GAMP, and we plug our magnitude and distance from disaggregation, and then with the site-specific VS30 results and do the ground motion selection. But the other type is today's focus, we do the site response analysis using the rock motion, which can either, again, from empirical ground motion prediction equation, or sometimes we can gather from those physics-based earthquake simulations to infer those rock motions. And the bottom right is cartoon just showing this idea that we will propagate the bedrock motions through our soil responsive soil column analysis to the surface level and continue our building analysis later.
So what we have right now is we want to take advantage of the SimCenter workflow and introduce kind of a site response module into the workflow. So the idea is to be able to propagate the motions from the bottom in a soil all the way to the surface, so that we can have the surface motions that can be used later in a model for a building. And the idea is to include nonlinearity in the soil so that we can capture this effect. For this, we need a tool to be able to do the analysis. We are choosing OpenSys in this case, but could be some other. And we need to be able to define this model. And for this module, what we are thinking about is a one-dimensional, 2-component kind of model that is based on finite elements. To develop the model, we need to have the depth to rock so that we can have the column height. We need to have some soil velocity model profile that defines the stiffness. We also need some information about the constitutive parameters for the different soil layers. And of course, if we want to include, for example, liquefaction, we need to know the location of the groundwater table. So this is our idea. So next, so what we what is important here is that if we want to do a regional analysis, we want to be able to develop these models automatically using a tool like R2D. And what we have currently implemented is something that allows at least to develop simplified models for these columns that include digital information about the depth to rock that can be obtained from maps, and also some information about the shear wave velocity, for example, using BS30 models from Wilson Thompson, and using some model for a shear velocity profile, like the one from Shi and Asimaki, then we can obtain the soil profile stiffness. Together with the depth that we obtain from the other plot. And what we have included right now is some way to include nonlinearity using a constitutive model that is proposed by Borja and Amis that allows us to capture G over G max curves. You have there one case where the parameters for this model have been optimized for a particular G over G max curve. And that G over G max curves allows you to get the nonlinear response that you see in the right bottom picture. So this is what we have, and with this we develop certain soil columns for Alameda, and then we perform some runs. So Kuanshi, can you continue from there?
Yes. So as Pedro mentioned, that we first get the rock motion from our has2 in the R2D, as Stephen introduced previously, and then we use those rock motion as our inputs to the soil column and analyze the column for every individual sites and get the surface motion. And on this slide, I'm just showing two examples for one site with two directions in X and Y direction, and the black curves are the rock motion time histories on the left two panel, and response spectra on the right two panels, and the red curves are the surface motion results. And typically in the R2D facilitated by its capacity and the remote run, we can increase the number of runs in every site and also enlarge our site coverage to the entire island. And I'm just comparing one very preliminary results that we got from I use Gampi prediction equation to get to the media PGA at given this ground motion or this earthquake scenario, versus if I use the same earthquake scenario to get the rock motion first, runs through our site response to get the surface PGA. So you can see there's a quite a difference in terms of the PGA fields on the surface level. And with this said, I would like to dive into the demo part of this R2D2 and to get some information about, get you familiar with our building information and the rock motion, surface motion intensity, and the building damage loss assessment. Let's just switch to the two here. So I'm just opening the R2D and load one example that's pre-run before to save some time. And so once you brought up, and we also share this same example with you in the assignment. So when you use the file open and then try to direct it to that shared file and open the example file. Let me just go into that folder for you. And open this input JSON file, you can just bring up the same page as I have now in the Vis tab. So on the Vis tab, on the left, you will see a bunch of column structure, tree structures for different GIS layers. And it's busy now. Let me just close a few of those. To just show first the ground motion input grids, as you can see here, we pick up a 6x6 ground motion grid, and at each grid we have 20 records selected. And if you don't want to have this cross grids, or you want to zoom in a specific region or zoom out, you can go always back to this ground earthquake scenario simulation toolbox to redefine a grid and run the ground motion simulation again. And then we'll, on the top of that, we have the soil grids here. We have 177 different sites, and for each you can click into a table and to know what's the longitude, VS30, and depth to rock information. And for our cases that we have the results, because I only include 6 cases to demo this, you will see the results that we see PGA, PGB, and also SA at 1 second for those completed analysis cases. And this just append the table as I see before without a run. And lastly, we get our building on the top here. So I'm just opening this again for the building layer. And I want to show you that some of the building that we have this, you can also follow in the same procedure as Steven mentioned, that you can look into the detailed individual building damage, but also you can back to the rest tab to get the overall statistic and figures for that. And from the detailed results table, you can scroll down to get each individual building asset damage or loss results. And with this said, let's back to our presentation here.
Yeah, so one thing that I want to emphasize is first how the site response module is integrated with the SimCenter workflow, and how the motion grid versus the site response grid versus the building grids, they are all independent. They can be, but then they are connected through the SimCenter tool. The other thing is similar to what Adam mentioned. In this simple example, we have 177 sites, 20 motions per site. So if you count, we have around 3,500 computations. And this site response analysis can be time consuming, particularly when they are when you go into the nonlinear regime. So it took around 6 hours using a personal computer when you run R2D in your own system. And it took only 50 minutes when we ran this directly, just pushing the button that Adam was mentioning, run in DesignSafe. So that really shows you the benefit of using a tool that is developed for SimCenter, but is connected also to other NERI centers like is DesignSafe. Now, one of the problems that we are having is that the model that we were considering here is quite simplified for Alameda. Alameda will show liquefaction, and just including nonlinearity in the stiffness would not be enough for this analysis. So what we have been doing lately is to develop a better model for the Alameda. So for that, using existing information from compenetration test and borehole reports, and then using typical tools to obtain the soil type from CPT, or to identify if which layers are liquefiable or not, using tools like CLeak, and then combining that with other models, like we did for the soil velocity model for Shia and Asimaki. What we have been doing is to develop a model for two things. One, so next is for the soil stiffness, a better model. So we have now a very good model for BS30 from the CPT database and USGS maps. From that BS model, we develop a 3D stochastic 3D model using kriging. And once we have the BS30 for any location that we are of interest, so we can change the grid for the soil layers, for the soil locations. Then we also use the soil velocity model from Shia and Asimaki. We can use other models. We know that Shia and Asimaki is only one. And then the other thing is the layering. And the layering is important because knowing the layers, we can identify which layer is liquefiable, which are the properties that need to be used for those layers. And once we had that, and we did, we also developed a 3D stochastic soil layer that defines the different thicknesses for these layers, again, using a kriging, in this case, with what is called an RBF kernel. And we use, one important thing is that we use the variance that we observe in order to add non-zero uncertainty to the thicknesses of these, or the location of these layers. And for that, we also use a beta transformation that is added to enforce upper and lower bound limits. So that allows us to create a 3D model for the Alameda Island. And here what I have is the Alameda Island. You see in blue, the location of the CPT data. And we did a cross-section of our model. And what you see in the picture below is that cross-section where you see the location of the different layers, how it changes across the island. And also you can see in dotted lines the different uncertainties that you can include. Why this is important? Because now what you can do is to interrogate the model at any location that you have of interest, and you can develop soil columns, 1D with 2 components, and you may have different realizations depending if you want to include also the uncertainty also in these layers. So that defines what we are trying to do in our next iteration of this application. So with that, Kuanshi, you're next.
Yes, so next we'll be doing another demo just to quickly show you the R2D's capacity to integrate those new model developments, and as a benchmark example, maybe also to can help or to motivate like a future collaborations and inputs from you. And I'm just want to demo that for R2D that we can currently just first to load that data table and to visualize and identify those layer information from a more refined model. So here I'm just back to our R2D2 and to the has tab, back to our original site response, in which we provide different ways to define a site and define a site grade. So we can do a single site grade locations, but now for the scatter locations, the previous example we just define a very single, very simple information for that. But in this case, I want to demo you to get this all layer soil information load into the table here, and you can also see the table attributes from this one, but we can navigate back to the Vis tab here. For the case, this is a relatively very dense grid that's covered on the Alameda Island. That's after Zach and Adam's work that's really help us to provide this example data results to show you today. And for this grid sites, let's see, if I just click into each data points here, you could get to the data table. On the right hand side, again, you could see the depth of the layer thickness of each individual layers from the top artificial fill layer down to the bottom merit sand thickness layer. And then now let's just do one quick example demo for you to, if I want to know what's the thickness of the first two combined layer. So what I will do is to get into my layer here and open in my attribute table. So you can see this is the entire table that we just load from our CSV data. And then we try to know what's the, create a new attribute here, new field. And then we just call it the combined layer thickness. And it will be a real number. And once it's created, it will append it in the end of the table. And then we will go into the attribute calculator and identify that one, click the expression. And here I know the true that the combined layer will be the summation of the first two. So what I will do is I will first use this conversion to convert the strand attributes that loaded in the fields from the first artificial layer plus my thickness of the second layer. And once I tap this down, you can see the preview here, and you can also load 10 samples to see the number. And once that's done, I can just click OK and update all. And then the information are automatically loaded here for the case. And now that I want to go into visualize the things, so I will just close this table and double click this layer and select the graduated. And in the value, I will do the combined layer thickness, the attribute that we just defined, and classify its range. You can see it's from close to very thin layer thickness down to close up to 41 meter. So once that's done, I can just click apply and click OK, and then just to remove some of those top layers to avoid the. So you can see if I zoom out, you will see this gradual plot showing where actually the deeper the thickness of the first two soil layers in the island. Yeah, so with this said, I just close this demo here, back to our presentation again. Yeah, so this is actually, as Professor Arduino mentioned, that's our current working efforts to the next step, try to get a refine the soil model to continue the efforts on the Alameda testbed. But in the meantime, the Alameda itself would be a place that can be mounted on several other possible options. So we also were happy to get your opinions and thoughts, comments, inputs to further develop an advanced simulation workflow to consider not only the ground shaking but liquefaction in the future, to create a test bed model for informing the local hazard mitigation plan, which is very important to the Alameda city itself, but create a model for all the places that can be learned from this example. And then initiate assessment of multiple systems like a building, bridge, and the pipeline networks that will go into the recovery analysis of this island as a model example again. And featured by those different options that's created in the SimCenter software package, that we can actually do some cross-model comparisons. For instance, at the hazard level, looking into different options, just like the previous slide showing, compare the GUMP versus soil responses for the damage loss assessment, comparing different options from hazards to PB to FEMA P58 or even more advanced detailed simulation-based methods. And we really, as the SimCenter developer team, really hope that you can be interested by these topics and have future collaboration and inputs with us, and we'll be really grateful. And with this said, I'm just closing our presentation today with a quick recap that the computational workflow we're trying now just to put together is preliminary, but it does have the feature that can be run at local or remote and have really optimized the performance on the parallel computing network, and then our module functionalities that really featured by the entire really smart and efficient computational workflow can help us to deliver the work more efficiently. And thank you so much for your attention today.